In the previous class, we have learned up to the order and the molecularity of a reaction in the chapter of chemical kinetics. Today we will start from the integrated rate equation. Integrated rate equation is there in the syllabus for two types of reactions. One is the zero order reaction, another is the first order reaction. So let us start with the number one type, zero order reaction. See, for zero order reaction, we know that here from a reactant product is produced, but in the case of zero order, the rate of the reaction is independent of the concentration of the reactant. So we can write rate that is equal to, we know, we have studied in the first part only, it's minus dA by dt, and that is the rate constant K, because it is independent on the concentration of the reactant. So we can write dA is equal to minus K dt, isn't it? Now we are integrating this equation on both the sides. So what we will get? A is equal to minus Kt plus I. I is the integration constant. Now you see, when the time was 0, that means the reaction has not started, then the total concentration of A was the initial concentration of A, and let us consider it as A0. That before the reaction started, the concentration of A was the initial concentration, and that is A0. So if we put T equal to 0 and A equal to A0, then what is I? The integration I becomes A0. Putting the value of I as A0, we get this reaction as A is equal to minus Kt plus A0. So what do we get? K is equal to 1 by T, concentration A0 minus A. So this is our integrated rate equation for a zero order reaction. Now if, see, what is this? This is the change in the concentration. So if I consider the change in the concentration as X, so what can we write? X is equal to Kt. So this is our zero order reactions integrated form, where the rate constant K is equal to 1 by T. T is the time taken, and A0 minus A is the change in the concentration. Okay. Now we will do two graphical representation for zero order reaction. See, for a zero order reaction, if I plot reaction rate versus concentration, the rate is independent on the concentration. So as the reaction rate and concentration is independent of each other, the graph will be a straight line. It is not dependent on the concentration. And if I plot the concentration of A with time, then obviously we will get a negative slope graph, because gradually with time the concentration of A is decreasing. So this is the two graphical representation for a zero order reaction. Now for a zero order reaction, what is the half-life? Not only for zero order reaction, half-life for any reaction is the time at which the initial concentration of the reactant taken becomes half its value. Suppose I have started the reaction with 100 mole per liter of reactant. The time at which the concentration becomes 50 mole per liter is the half-life of that particular reaction. So we represent half-life by T half, the time taken for the reactant to become half its concentration. So if the initial concentration is A0, in half-life the concentration of A will be become what? The half of A0, that is A0 by 2. So at half-life, T half becomes A0 by 2K. Okay, in this expression I am bringing T here and K here, so it becomes A0 by 2K. So this is the expression of half-life for a zero order reaction. So if we plot for a zero order reaction T half versus A0, the concentration, then we get a straight line passing through the origin, where the slope of the graph is equal to 1 by 2k, where 1 by 2k is the slope. So this is the graphical representation of the half-life for a zero order reaction. Now comes the integrated form of the first order reaction. See, for a first order reaction, suppose a reaction is taking place A plus B to product. Whatever may be the reaction, for a first order reaction, rate is always equal to the rate constant, and it depends upon the concentration of any one of the reactant. Suppose it's A, then if A is our reactant on whose concentration the rate is dependent, let the initial concentration of A is equal to small a mole per liter. When the reaction has not started, A to product, when the reaction has not started, product is 0. Now in the course of time, the product has formed X mole per liter, then what will be the concentration of A? A minus X. X amount of product has formed and A got reduced to A minus X. Then what will be the rate of the formation of product? dx by dt will be equal to the rate constant K into the concentration of the A. It is the rate of the reaction is dependent upon the concentration of the reactant, that is A minus X. And what is the rate of the formation of product? dx by dt. So we can write dx by dt is equal to K into A minus X. Now if I bring A minus X here, that is equal to the K dt. Now this expression I am integrating both the sides. What we get? Minus ln A minus X is equal to Kt plus I. Again, I is the integration constant. Now see, when time t is equal to 0, x is equal to 0. So putting t0 and x0, what I get? I is equal to minus ln A. Putting the value of I in this expression, what I get? Minus ln A minus x is equal to Kt minus ln A. So K is equal to 1 by T ln A by A minus X. If I convert ln to log, what I get? 1 by T into 2.303 log A by A minus X. That is our rate constant K, and this is our integrated form of the first order reaction. This is our integrated form for the first order reaction. Okay. Now you see, from this integrated form we can plot two graphical representations we can have. Two types of graphical representations are there. We got the integrated equation as this one, and we want to plot log A minus X versus T and log A by A minus X versus T. So this one will be easier. See, from this equation, if I keep log A by A minus X on one side, what we get? Log A by A minus X on one side I want to keep. So what I will get? Equal to Kt by 2.303. So for this case you can see that this is our y and this is our x. In the form, in the mathematics we have done y equal to mx plus c. Here y is the log A by A minus X and x is our t. So we don't have any intercept and the slope is also positive. So in this case the graph will be a straight line passing through the center, where the slope is equal to what? K by 2.303. Our slope is K by 2.303. But in this case we want to plot only log A by A minus X. From here I want to take Kt by 2.303 is equal to, we can write log A minus log A minus X. So keeping log A minus X on one side as y, what can we write? Log A minus Kt by 2.303. This is our expression. Again, from y equal to mx plus c, y is this one and x is our t. So we have an intercept and the slope is also negative. So we will get a negative slope and having an intercept. This is our intercept. The value of the intercept is log A and the value of the slope is k by 2.3 minus k by 2.303. So this is our two graphical representation of the integrated form of the first order reaction. Now I will come to the half-life of the first order reaction. Again, as I told, half-life is the time taken for any of the reaction to come to the half the concentration of the reactant molecules. So here X will be equal to A by 2, half the reactant molecules concentration. So T half, from this expression I am bringing it, T I am bringing here, T half is equal to 2.303 by K log A by A minus A by 2. So what it is coming? 2.303 by K log 2, and 2.303 into log 2 is 0.693 by K. So for a first order reaction, T half is equal to 0.693 by K. This is the half-life of a first order reaction. All these formulas are essential in doing the numericals from this chapter. So either you can derive it or you can directly memorize the formula and apply it during the time of doing the numericals. Another type of expression is there where we can write TF is equal to 2.303 by K log A by A minus FA. Now you see what is this F denotes. F here means that the fraction of the reactant molecules decomposed. You see, in many numericals it is not necessary that always it will be asked for the half-life. Suppose it is told that the 50% of the given quantity of reactant has been decomposed, or 25% of the reactant has been decomposed. If the amount is different from 50, it can be 75, it can be 63, it can be 25%, then F represents the fraction and FA is the amount of the reactant decomposed, or in general we can write 1 by 1 minus F, where F is the fraction. Another time you see, another expression I want to tell, amount of substance left after n half-lives. What is it? See, suppose we have started with the amount of the reactant A. Now after one half-life, how much of the reactant has been left behind? A by 2. Then A by 2 becomes our initial concentration, and for A by 2, what will be the next half-life? After next half-life amount of the reactant? Half of A by 2. Again, this is our initial concentration, and what will be the reactant left behind after another half-life? Half of A by 4. Again, it continues in this way. So we can see that after n number of half-lives, the amount of the reactant left behind becomes A by 2 to the power n. For one half-life, 2 to the power 1. For two half-life, 2 to the power 2. For three half-life, 2 to the power 3. So in this case, for n half-life, the amount of the reactant left behind becomes 2 to A by 2 to the power n. Next, the last part of this chapter that I want to discuss about is very important part, Arrhenius law, which involves the relation between the rate and the activation energy. Before I come to the law, I want to tell about what do you mean by activation energy. For any reaction, activation energy is the energy required to start the reaction. For each and every reaction, there is a definite amount of energy that we have to provide from outside for the reaction to take place. If I represent graphically, suppose this is the amount of the energy of the reactant molecule already there. But for the reaction to take place, it has to pass through an energy of this level. So this is our reacting state of the reactant molecules, the state at which the reactant molecules will start reacting. And after the reaction, this is the energy of the product. So this much amount of energy already the reactant molecule is having, but we have to provide extra this much amount of energy for the reaction to occur. So this is our activation energy which we have to provide to the reactant molecules for the reaction to occur. Once the reacting state has been attained, the reaction will take place automatically. So activation energy is the energy that we have to provide from outside for a reaction to take place. So the rate of the reaction K is equal to the A into e to the power minus EA by RT, where K is the rate constant, A is the frequency factor. What is the frequency factor? Frequency factor is the frequency of the collisions of the reacting molecules that is occurring during the reaction. The amount of collision that a reacting molecules is undergoing, that is the frequency factor. EA is the activation energy, R is the universal gas constant, and T is the absolute temperature. So this is our Arrhenius equation. Now I will simplify it. Let me take ln in both the sides. Then ln K is equal to ln A minus EA by RT. If I take a log, then what I will write? Log K is equal to log A minus EA by 2.303 RT. You see, now if I plot a graphical representation of log K versus 1 by T, what type of graph I will get? This is X, 1 by T is, this is Y, and 1 by T is the X. So we have an intercept and a negative slope. So this will be our graphical representation, where the intercept is log A and slope is equal to minus EA by 2.303 R. So you see, by plotting a graph and from the slope of the graph, we can get the value of the activation energy. Again, in some numericals, it will be given to calculate activation energy. Two rate constant value will be given at two different temperatures. That is, this is our general expression. So suppose it is told that at temperature T1 the rate constant is K1. So what we will write? Log K1 is equal to log A minus EA by 2.303 R T1. Again, for temperature T2 the value of rate constant is equal to K2. So we can write log K2 is equal to log A minus EA by 2.303 R T2. So evaluating both the cases, we can cancel out log A and we can have the expression log K2 by K1 is equal to, I am taking EA by 2.303 R common, then in a third bracket I can write 1 by T1 minus 1 by T2. So while doing the numericals, we can directly apply this formula where K2, K1, T1 and T2 will be provided, and we have to calculate the value of the activation energy EA. If you don't want to memorize the formula, you get the initial expression, derive this, and you can also do the numericals. So in this chapter, this is the theoretical portion of chemical kinetics. Based on this, I have given you some numericals as homework. You try to do the numericals, and if any problem, in another class I will discuss about some numericals on this chapter, chemical kinetics.